Okay, I'll be talking about some results on boosting, so on multiclass boosting. So boosting is a method for combining a lot of weak statistical signals into a strong statistical signal. And like any other machine learning algorithm, the focus is to create models that both well fit training data as well as have low complexity. Having low complexity ensures that we don't overfit, and fitting through the training data ensures that we don't underfit. What it means for boosting is that the weak classifiers or weak signals that are combined should also have low complexity, but not too low complexity, so that we both avoid overfitting and underfitting. Now, the right notion of complexity for weak classifiers is well understood in the case of binary boosting, but this is not very well understood for multi-class boosting, and in this work we sort of fix the gap. So for binary boosting, the right complexity of weak classifiers is the following. Those weak classifiers should be able to do slightly better than random guessing on any distribution on the training set. Clearly, nothing weaker is going to be sufficient, and anything stronger than that is not necessary. And that's what the results say. On the other hand, if you try to extend that directly to multi-class boosting, we run into problems. For instance, just doing better than random guessing on any distribution leads to two weak conditions. Doing better than 50% accuracy, if you think 50% was the right number, since in binary boosting we do better than 50%, leads to two strong conditions. Other approaches have relied on reductions to binary, and that turns out to again lead to occasionally stronger conditions. For instance, one against all, the popular one against all multi-class reduction technique leads to two strong conditions. So what we create is a new framework within which we can even capture the right notion of weak learning. I guess I'll have to ask you to read the paper for the details, but essentially, instead of sending distributions, the booster sends cost matrices in each round, with which it can exercise more fine-grained control over the weak learner. And here are some results where we compare our boosting algorithm using the minimal conditions necessary for boosting against boosting algorithms which use stronger than necessary assumptions. And what we find is that, the x-axis measures the complexity of the weak classifiers used, and the y-axis the error, and we find that our boosting algorithm achieves lower accuracies consistently across many data sets when used with extremely weak classifiers. Yeah, thanks.